Presented by Caltech.
Earlier this year, Caltech scientists announced the probable presence of a ninth planet. We are lucky to have one of the paper's authors as our general session speaker today. Dr. Batygin was born in Russia but received his education in multiple places, but he got his undergraduate degree at UC Santa Cruz, but he got his master's degree and his PhD here at Caltech. And I think he's never left. In 2015, Konstantin landed a spot on Forbes' list of 30 under 30 young scientists who are changing the world. The magazine called him the next physics rock star. It is a most apt description, since in addition to spending time with his wife and young daughter, he moonlights as the lead singer in the band The Seventh Season. It has been my great pleasure to get to know this very engaging young man and to introduce him to him today. He will be addressing why he and his colleagues think there is probably a ninth planet in our solar system. Dr. Batygin.
All right. How do I turn this on? Can you hear me? Oh, excellent. All right. Well, it's my true pleasure to be here today. I'm delighted and frankly starstruck and humbled to be talking to this group of people. So today I'd like to take a few minutes to talk about, well, maybe a few tens of minutes to talk about a subject for which I've developed quite an affection, which is the orbital architecture of our own solar system, in particular its most distant realms. Now, astronomy, of course, being sort of one of the oldest forms of natural science, has enjoyed a long and dramatic history, but it was only kicked into high gear, astronomy as we know it in current form, really 400 years ago when Galileo adopted the telescope and we became no longer limited by the resolving power of the human eye. And what's further fascinating is that despite the kind of breaking down this limitation, the search for additional faint wandering stars that walk around the night sky has been pretty unproductive in the solar system. In the last 400 years, sheer numbers-wise, we've only discovered 2 planets that the ancient civilizations were not aware of. And the first such planet was discovered actually during the American Revolutionary War in 1781 by Sir William Herschel, and he called it George. So you can have Jupiter, Saturn, George. And the international astronomical community of the time said, that's a bad name for a planet, so let's call it Uranus, because that's a better name. So the fascinating thing is that almost immediately, astronomers and mathematicians of the time noticed that George was not behaving correctly. In fact, George was doing the wrong thing. Its orbit was reconstructed upon discovery from previous kind of serendipitous observations when astronomers drew it but didn't recognize that it was an actual moving star. And they noticed immediately that it was deviating from its purely envisioned Keplerian orbit. And Alexis Bouvard, who was the director of the Observatoire de Paris, in 1821 published this set of astronomical tables, which I'm sure is apparent from this slide. There is cosines and sines on the left-hand side and a table on the right-hand side. And what he pointed out was that, look, it's just, if you combine all of the observations of the time together, there's no way to reconcile Uranus's orbit with just the 2 perturbing big planets, Jupiter and Saturn. So as a good theorist, he didn't rule out the possibility that the data is crappy. But he also speculated somewhere in here, I don't speak French, so I'm only guessing that it's in the overall this slide, that perhaps there's a different additional massive planet that lives beyond the orbit of Neptune. And it wasn't for an additional 2 decades before the promise of Bouvard's data really came to fruition, and it was It was really worked out by this guy, Urbain Le Verrier, who lived between 1811 and 1877, who took this idea, right, that there's a different additional perturber residing in the solar system, and worked it out. So by probably with a lot of wine and a lot of papers in his Parisian apartment, he just worked out and predicted the existence of Neptune beyond Uranus. Now, when I was an undergrad in Santa Cruz, I lived in sort of a shady part of town, so I can spot a gangsta from afar. And this guy is clearly a gangsta, you can tell, because he's wearing his bling on the outside, right? It's important, his stage name is Urban Le Verrier. I mean, he's a gangsta. So this is actually part of the manuscript where he details the derivation of how to resolve Uranian irregularities with introduction of Neptune. And what he also proved was that I don't have the worst handwriting in astronomy in history. So what's remarkable is that after this discovery, which took place in 1846, and by the way, Neptune, when it was finally observationally confirmed, it was confirmed in just a single night of observation. Gall, who was an observational astronomer in Berlin, sort of made this multi-year campaign to look for Le Verrier's predicted planet, and opened up the telescope and said, oh, well, there it is. So it was kind of one of the most remarkable examples of where theory meets observations. But in the last 170 years, despite numerous attempts to relive and reconstruct these types of calculations, the solar system has failed to produce additional planets. What we have found, however, is a field of debris that lives beyond the orbit of Neptune. So there's Mercury, Venus, there's Earth in blue, my house right here. There's Mars, Jupiter, Saturn, Uranus, so George, Neptune. This big blue thing is the orbit of Pluto. I don't know why it's there. It's, P for Pluto, P in Pluto stands for not a planet. Pluto really is smaller than the moon, so I think it's correct that my friend and colleague, Mike Brown, really pulled the plug on its planetary status. But what's interesting is Pluto, it turns out, is just one fragment in this big belt of debris, which we now collectively call the Kuiper belt. What we will see shortly are all of the orbits of the Kuiper belt, and when we turn our viewing angle back to sort of a top view, you'll see that the Kuiper belt has this unifying feature. And this unifying feature is that most of these orbits these orbits, virtually all of them, are tethered to the orbit of Neptune, right? They physically hug the orbit of Neptune. The reason this is the case is that Neptune was the thing that produced the Kuiper belt, right? The gravitational potential is conservative, so if you're Neptune and you kick an object, it's going to go out on its elliptical orbit, but it's going to come back to exactly where it started from. So that's why all of these orbits hug the orbit of Neptune. So when the Kuiper belt was first discovered, one of the kind of key elements, key things that we learned was that it totally makes perfect sense, right? Its orbital structure is complicated, but it can all be understood within the framework of our 8-planet solar system. We even learned things about how our solar system formed from mapping out the structure of the Kuiper belt, except for one object. And this one object was discovered by my friend Mike Brown back in 2003. This object is called Sedna, 2003 VB12. Right? So you can immediately, you don't have to be an expert in the Kuiper belt to understand that this is different from this, right? Sedna, at its furthest point, goes out to almost 1,000 times the distance between the Earth and the Sun. So it's got this exceptionally elongated orbit. What's even more remarkable about its orbit is that it's not elongated enough, right? At perihelion, it doesn't hug the orbit of Neptune. Neptune could not have, by itself, produced this object. So back in 2003, with data point of 1, there was quite a bit of speculation. Maybe this was an object that was dropped off by a passing star. Maybe there's a Earth mass planet over here or over here. You know, with one data point, it's hard to say anything useful. But it was really 2 years ago when I just started here as a professor. As was already mentioned, I was a grad student here before that. So when I came back as a faculty member, you know, Mike and I sort of got back to work together. And really, he was the one who pointed me to this and said, let's figure out what's going on in the distant solar system. So really, the first thing we noticed was that if you just look at the most distant orbits in the solar system, of which there are now 6, there are now 6 Sedna-like orbits, they all kind of point to the left, okay? And moreover, they all sort of lie in the same plane. So if we put ourselves in the ecliptic plane, you can almost envision putting a piece of paper through that collection of orbits. And you know, if you've ever done an open water swim, right, you'll have good intuition for isotropy, right? There's no reason why all of these orbits should point in one direction, right? In fact, you know, it's surprising to me that this point had eluded the field for as long as it had. So we thought, okay, well, maybe, just maybe, this is just observational bias. Maybe observers, you know, only looked in that part of the sky and somehow picked out orbits that all point to the same direction. Turns out, each one of these guys was discovered by a different survey, different telescope even, with different observational biases. Thought maybe we got lucky. Maybe we just happened to pick out 6 orbits and, you know, they all sort of happen to point in the same direction. And of course, you can evaluate the statistical significance of that. You can evaluate the probability that this is all by chance. And that clocks in at 0.007%. So it's not a great gamble. Some of the quantitative investors will you know, can comment further on this. And importantly, this could not be some relic from the past, right? If you invoke some stellar encounter during the sun's birth, you would not see this observed structure, because if you just leave these orbits alone under the influence of the known giant planets, in a few 100 million years, they will randomize. So something is keeping them together right now. So in the next couple hours, I want to go through this derivation. And, you know, I usually put up this slide as a joke, you know, but I'm guessing this is the wrong audience to be joking about this, because you guys might actually enjoy it. But the point here is that, you know, you can get started in virtually the same way that Leverrier had. You can do perturbation theory and come up with a Hamiltonian, which provides a pretty good approximation to the long-term evolution of these orbits. And what you can learn just by doing stuff on the board is that if there is indeed a planet, it has to be pretty massive. It's got to be at least a few times more massive than the Earth, more like 10. And its orbit will be unlike the orbits of the planets that we have grown to know and love. It will be highly eccentric. So despite the feeling you might get at times watching the news, it is no longer 1846. So we don't have to do the entire calculation on paper. We can resort to the vast and awesome computational resources that we have here at Caltech. So we decided to do a bunch of evolutionary calculations, right? Let's start the solar system in the configuration that it had 4.5 billion years ago, when the Kuiper belt just formed as this axisymmetric collection of eccentric orbits, and evolve it forward in time under the influence of the known planets plus a putative planet 9. So we ended up doing just a ton of these calculations. So there's no shortage of bad results. If you guys are ever in need of bad results, I can provide you with bad results. But what we began to notice is that, much like what those analytic calculations had suggested, if you put a 10 Earth mass planet on an eccentric orbit whose perihelion, closest approach to the sun, is at about 250 AU, 250 times the distance between the Earth and the sun, over a period of 4 billion years, what this planet will do is it'll start carving out a population of orbits which will, in the end, resemble the ones that we really have. And it's a fascinating thing because it actually does take 4 billion years for this for the structure to emerge. It's right around now, which is about 2.5 billion years into the evolution, that you begin to see that only the orbits that are anti-aligned with respect to the orbit of the planet are surviving, and there's still some stragglers over here. So, every time I watch this, I know what the final answer is, but I'm still like, will it really happen? Will it really happen? So to quote Kanye, I'm gonna let you finish. So, yeah, in the end, the thing you produce is that these gold orbits are like the conventional Kuiper belt, right? They're evenly distributed, and these distant guys are anti-aligned. One of the things that surprised us right away, both Mike and I said, how the heck are these things stable? Right? All of these orbits intersect. How do they avoid suffering close encounters with Planet 9 and getting ejected? In the end, that's how the rest of the orbits got ejected. What's keeping these guys confined? And the answer, as it turns out, can be deduced from our insignificant friend Pluto. Pluto also crosses the orbit of Neptune, but is protected from ever coming too close to it, suffering close encounters by a mean motion resonance, meaning that Pluto's orbit and Neptune's orbit share this clockwork-like relationship where for every 3 orbits that Pluto completes, for every 2 that Pluto completes, Neptune completes exactly 3. And so they kind of avoid seeing each other. And as it turns out, all of these orbits are resonant with Planet 9, only this time the resonances are much more exotic and are in fact chaotic. So if you leave this system alone, they maintain the overall orientation, but the orbits are changing in an unpredictable manner all the time. So at this point, we had a pretty good sense for what the orbit of Planet 9 would look like. Based on the real objects, we derived that it's got to be like this. We know that it's not in the closer half, maybe closer 2/3 of its orbit. Presently, it's closer to aphelion. That's what you would expect anyway from a Keplerian orbit, because by Kepler's second law, you spend most of your time far away from the sun. So we felt pretty good about ourselves, and then we ran into this total block, which is nicely summarized in this slide. This is a huge problem, right? What we have here is on the x-axis, this is basically the azimuthal orientation of the orbits. On the y-axis is the orbital inclination. And what we noticed is that every time we reproduce our cluster of distant things, in the solar system, we also produce a population of orbits that had been twisted on their side. It was orbit the sun in an almost perpendicular sense compared to the disk of the solar system. And I'm just a simple theorist, but I remember learning in elementary school that in the solar system things go roughly like this. They don't go like that. So I was really stumped, and Mike was stumped for a little bit, and then Mike said, "You forgot about 2012 DR30." And I had indeed, well, I'd never heard of 2012 DR30, but I thought maybe that was an experimental drug or something. And what Mike said, I remember learning that 2012 DR30 has an inclination of 78 degrees. Okay. So what we did, one afternoon in his office, we said, okay, let's put all of the model predictions and just do the honest thing, not look at the data, and then let's plot not just the Kuiper belt data, but all of the data that we have in the solar system, small body catalog. And what we found is that indeed there exist these little guys, these tiny pieces of debris that orbit the sun in an almost perpendicular sense. And they had all been discovered only within the last couple years entirely by accident. They had been discovered by a near-Earth asteroid survey because the near-Earth asteroid survey does not discriminate based upon where in the sky the killer asteroid will come from. Right? It's going to be a very embarrassing last couple hours of your life when you kind of try to explain to the world, you know, we searched over there and there was no killer asteroid, but it came from over there, right? So this is a stark contrast with Kuiper belt surveys. Kuiper belt surveys only look in the ecliptic plane, which is why these objects had eluded observation. So as it turns out, what our model was predicting, this population of perpendicular orbits, it really is out there. And I think this is actually the strongest line of evidence for the existence of Planet 9, because there's no other way in hell to produce orbits in the solar system that are twisted up. So this is what they look like in real space. These are the real objects. Notice that this guy over here is even more extreme than Sedna, right? We thought Sedna was weird. This guy has a semi-major axis greater than 1,000 AU. So out here, it's going out to almost 3,000. Quite an incredible set of objects. We have now, by the way, I'm going to send myself on a tangent. We've understood the physics by which this twisting happens, and it's an effect which had actually been known since the early 1960s, called the Kozai effect, and had been pointed out in the asteroid belt as well. But even before that, it had been pointed out by a Russian guy named Lidov in the late 50s, because the first Russian satellites came crashing down into the Earth's atmosphere because the potential of the average kind of mean field potential of the moon would twist them and make them more eccentric. So when we published the paper, we cited the Kozai paper, but not the Lidov paper. And I got an email recently from a Russian guy that said, "Come to Kaliningrad, I punch you in the face." So on that note, what the heck is Planet 9? Planet 9 is an object which looks, until it's caught on camera, I can make up what it looks like. And it looks exactly like this. It's got 1, 2, 3 lightning storms. It's got an orbital period of 20,000 years, a mass about 10 times that of the Earth. We actually have constrained this number pretty well since the original publication. We really do think it's 10. It's not 20. It's not 5. The radius we must only guess based upon radius mass relationships that exist for planets around other stars, exoplanets, but we think it's kind of like Neptune's, between 2 and 4 Earth radii. It's got a wildly eccentric orbit, 0.6, which is quite in a stark contrast with the rest of the nearly circular orbits of our planets, quite inclined as well. And it's got a visual magnitude of 24. So if you're an astronomer, I think I heard somebody go, ooh. So visual magnitude 24 is pretty dim, okay? But it's not as dim, it's not so dim that it's undiscoverable. In fact, there's basically one telescope on Earth that is perfectly suited for the observational search for Planet 9. And it's this guy right here, the Subaru telescope, Japanese National Observatory. It's an 8-meter telescope, and 24th magnitude is well within its capabilities given, so we'll have to have about 20 nights on the Subaru telescope to complete our search area. So this is Mike and myself in the Subaru dome. It's huge. I never really observed before, and I didn't appreciate the extent to which this thing is a behemoth. And because you guys are my home crew, I'll tell you where Planet 9 is. So this is the night sky, I'm told, and this guy right here is the Orion constellation. My cat's name is Orion, so this is one of the constellations that I actually do know. And over here, this star goes through Orion's shield. Now, depending on which which picture of Orion you look at is either holding a sword or a shield, or sometimes a bow. But Planet 9's aphelion is right here. So that's where you got to look. Okay? So this way you guys can tap into your inner hipster for when it's found. Say, oh yeah, I knew it was rare. I knew it was way before it was popular. A couple last thoughts about Planet 9. What does Planet 9 mean for our solar system? Well, it turns out Planet 9 is the least weird thing about our solar system. It's the thing that makes our solar system fit in better into the galactic planetary census. With its high eccentricity of 0.6, it fits better into the overall orbital distribution of planets in general than our circular orbits that scrape the bottom of this plot. In the last 20 years, we've discovered more than 3,000 planets that orbit other stars, and they don't tend to look like the solar system. We are the anomaly, so to speak, and Planet 9 is perhaps our link to the extrasolar world. I sometimes like to say that the Planet 9 is our solar system's exoplanet. And final thought is that the thing that kept us up at night was that maybe we made all of this up, right? I mean, that's kind of, as a scientist, you try not to believe yourself too much, and we thought maybe we, kind of subconsciously constructed all of our statistics to tell us that indeed this is all relevant. And after all, statistics is just another way that human beings lie to one another. So we were really worried that the next set of orbits that would be discovered in the Kuiper belt would make this cluster go away, and then we'd be pretty embarrassed. But the good news is, since then, objects have been discovered, and they all fall exactly where our model predicts them to be. This is an example of a new orbit that's been discovered by a Canadian survey. The reason the picture looks so bad is that somebody in Mountain View took a picture of somebody else's talk and then posted it on Twitter, and then I screen captured the Twitter. So that's the true new methods of celestial mechanics. I'm not going to go through this. I will simply put up a picture. This is my friend, mentor, and colleague, and sometimes workout buddy, Mike Brown, with whom I have the pleasure of working. And also, I wanted to acknowledge people working in my group: Catherine Deck, Chris Spalding, Henry No, Natalia Storch, Peter Buehler, and Elizabeth Bailey. They were not directly involved in this work, but still, my daily experiences at Caltech would not be the same without the awesome, dynamic conversations that I have with these guys and girls. They're awesome. So at this point, I want to say thank you.